Welcome to the second lecture on the algebra of matrices. In this lecture, we introduce a multiplication between matrices of appropriate sizes. We begin by reviewing the content of our first lecture on matrices. An m by n matrix is a table of scalars with m rows and n columns for some non-zero natural numbers n and m fixed throughout this lecture. We index the cells of the table first by their row position, then by their column position. We also regard an m by n matrix as a family of n vectors in k to the m listed as the columns of the matrix. The jth column of A thus consists of the m tuple formed by the entries on the jth column of the table for j any integer between 1 and n. We use a standard notation for the set of m by n matrices with entries in the field K. The set of m by n matrices with entries in a field K is technically the space of functions 2k from the product of the set of integers from 1 to m by the set of integers from 1 to n. Thus, it has a natural vector space structure, where the operations are entry-wise. Thus, we add two m by n matrices simply by adding their entries, and we scale an m by n matrix A by a scalar lambda by multiplying each entry of A by lambda. Note that we only define the addition of matrices between matrices of the same size. The neutral element in the space of n by n matrices is the matrix whose entries are all equal to the scalar 0. Note that there are technically many zero matrices, one for each size. If needed, we index our zero matrix by its size, though we will take the habit to simply write 0 for all zero matrices. The fundamental observation we made in our previous lecture is that it is natural to define a multiplication of an n by n matrix with a vector in k to the n. If a1, etc. an are the columns of an m by n matrix A, and if x is a vector in k to the n, then a times x is a vector in k to the m, defined as x1 times a1 plus x2 times a2 plus etc. plus xn times an. This product has several properties which are easy to check but very important. First, we observe that if lambda is a scalar, if A and B are two m by n matrices, and if x is a vector in k to the n, then lambda A plus B, applied to x, is lambda A times x plus B times x. Second, we observe that if A is an m by n matrix, if x and y are vectors in k to the n, and if lambda is a scalar, then A times the vector lambda x plus y is lambda A times x plus A times y. In other words, an m by n matrix A defines a linear map from k to the n to k to the m using this multiplication operation. Let us denote this linear map by T sub A. We thus define a map T from the space of m by n matrices to the space of all linear maps from k to the n to k to the m. As we have just seen, this map T is actually linear. We saw in the previous lecture that T is in fact a linear isomorphism. Let us present a proof once more. Let E1, etc. En be the canonical basis of k to the n. The image of E sub j by T sub A is the jth column of A for all integer j between 1 and n. In particular, the function T sub A is a constant zero function if and only if the matrix A is the zero m by n matrix. In other words, the kernel of the map T is a singleton 0. Thus, T is an injective linear map. Since the dimension of the space of all linear maps from k to the n to k to the m is n times m, which is also the dimension of the space of m by n matrices, we conclude that T is in fact a linear isomorphism. The inverse map of T is important. We denote it by mat. Its domain is the space of all linear maps from k to the n to k to the m, and its codomain is a space of m by n matrices. Let us describe this function as we did in our previous lecture. Let phi be a linear map from k to the n to k to the m. The matrix of phi is the m by n matrix whose columns are the images by phi of the vectors in the canonical basis of k to the n. More formally, if E1 etc. En is the canonical basis of k to the n, then the matrix of phi is the unique m by n matrix such that the matrix of phi times the vector E sub j is the image by phi of the vector E sub j for all integers j between 1 and n. We indeed check that mat, thus defined, is the inverse of the map T. As T is linear, so is the map mat. For the rest of this lecture, and for future lectures, we record the following two consequences of our work so far. First, if phi is a linear map from k to the n to k to the m, then phi is actually the function which multiplies a vector in k to the n by the matrix of phi. Second, if A is an m by n matrix, then A is indeed the matrix of some linear map phi. In fact, phi equals T sub A. Now, there is an operations on functions with appropriate domains and codomains, namely composition. We use the idea of transport of structure to define an operation on matrices which will make the map mat a morphism between composition and this new operation. In other words, we address the following question. Let phi be a linear map from k to the n to k to the m, and let psi be a linear map from k to the m to k to the r, where r is a non-zero natural number. Let us simply write A for the matrix of phi and B for the matrix of psi. Note that A is an m by n matrix and B is an r by m matrix. The question is, what is the matrix of the map psi composed with phi, which we know to be a linear map? Well, its matrix is an r by n matrix, but how do we compute it? To answer this question, first note that if y is a vector in k to the m, then by definition, psi at y is b times y. Similarly, if x is a vector in k to the n, then phi at x is a times x. Therefore, psi composed with phi at x, which is psi at phi at x, is b times phi at x, which is therefore b times the product of a by x. To compute the matrix of psi composed with phi, we then apply this computation to the canonical basis of k to the n, which we denoted E1 etc. to En. Thus, if j is an integer between 1 and n, the jth column of the matrix of psi composed with phi is b times a times e sub j. Now, a times e sub j is a jth column of A. Thus, the jth column of the matrix of psi composed with phi is b times the jth column of A. We thus have a natural description of the matrix of psi composed with phi. It is the matrix whose columns are computed by applying the matrix of psi to each column of the matrix of phi. let us formalize this concept. The product AB of an R by M matrix A with an M by N matrix B is a matrix whose jth column is the product of the matrix A by the jth column of B for all integers j between 1 and n. Note that this product is actually an R by N matrix. We have thus defined a multiplication between certain matrices. We make a couple of remarks about this very important definition. First, note that we only defined the multiplication between matrices of certain sizes. Indeed, multiplication between A and B is only defined when the codomain of the linear map T sub B is the domain of the linear map T sub A. Second, and following on our first remark, the multiplication is trivially non-commutative. It is not even defined symmetrically. In fact, even for square matrices, that is n by n matrices, the multiplication is not commutative. We will return to this matter in our next lectures. As we have discussed at length, the fundamental property of the multiplication of matrices is the following theorem. If phi is a linear map from k to the n to k to the m, and if psi is a linear map from k to the m to k to the r, then the matrix of psi composed with phi is the product of the matrix of psi by the matrix of phi, in this order. The proof of this theorem is in fact the work done on our previous slide. We now study the basic properties of this multiplication of matrices. The right way to do so is to continue to exploit the fundamental relation between our multiplication and the composition of linear functions. We begin by showing that this multiplication has some neutral elements called identities. For each non-zero natural number n, we let I sub n be the matrix of the identity function of k to the n, that is, the function which maps any vector x in k to the n to itself. Sometimes we simply write 1 sub n for I sub n, or even just 1, if no confusion may arise. We also call I sub n the identity matrix or the unit matrix of size n. We note that it is a square matrix. It has as many rows as columns. We can compute I sub n explicitly. If j is an integer between 1 and n, the jth column of I sub n is a vector obtained by applying the identity function to the jth vector in a canonical basis of k to the n, so it is the jth vector in the canonical basis of k to the n. Thus, the columns of I sub n are simply the vectors in the canonical basis of k to the n. We thus get a diagonal of entries all equal to 1 and all other entries equal to 0. By construction, the product of a m by n matrix A and the identity I sub n is A. We could perform the computation by hand, but it is much better to simply observe that A times I sub n is a matrix of the linear function T sub A composed with the identity, which of course is just T sub A, and thus A times I sub n indeed equals A. The same reasoning applies on the left. We simply have to pay attention to the size of the matrices we multiply. We now move on to the basic algebraic properties of the multiplication. We first prove that the multiplication of matrices is associative. Let A be a P by R matrix, let B be an R by M matrix, and let C be an M by N matrix. Then A times the product of B and C is the product of A and B times C. Note that this statement makes sense. The product of B and C is an R by N matrix, so we can multiply it by A on the left to get a P by N matrix. On the other hand, the product of A with B is a P by M matrix, which can be multiplied on the right by an M by N matrix C, again to get a P by N matrix. To prove this result, we need not do any complicated computation. Instead, let alpha be the linear map from k to the r to k to the p whose matrix is A, that is, alpha is T sub A. Similarly, let beta be T sub B, that is a linear map of matrix B, and gamma be T sub C, that is a linear map of matrix C. Thus, by the fundamental property of the matrix multiplication, the product of B with C is a matrix of beta composed with gamma. Then, A times the matrix of beta composed with gamma is a matrix of alpha composed with a composition of beta and gamma. Now the key observation, which is actually very easy to check, is that composition of functions, linear or not, is associative. So A times the product of B with C is indeed the matrix of the map obtained by alpha composed with beta first, then composed with gamma second. We then unwind our products using the fundamental property of the matrix multiplication. Doing so, we end up with the desired identity. Thus, the associativity of the multiplication of matrices is actually a direct consequence of the associativity of the composition of functions. We then prove that our multiplication is distributive on both the left and the right. Once more, we do so using the relation between matrix multiplication and composition. Let A be an R by M matrix, and B and C be two M by N matrices. Let also lambda be a scalar. Then A times the matrix lambda B plus C is lambda times A times B plus A times C. A similar relation holds on the left. We invite you to check that the size of the various involved matrices are indeed consistent. The proof follows a similar pattern as a proof of associativity. Let alpha, beta, and gamma be the linear maps of respective matrices A, B, and C. Thus alpha is T sub A, beta is T sub B, and gamma is T sub C. We also will make use of the fact that the map which sends a linear function to its matrix, that is, the map mat, is itself linear. Thus, A times the matrix lambda B plus C is the matrix of alpha composed with lambda times beta plus gamma, which is the map lambda alpha composed with beta plus alpha composed with gamma. Here we use the fact that alpha is linear. We then use linearity of mat to conclude the desired identity. The proof of distributivity on the left is similar. As a simple corollary, which we just state for the record, we note that we have proven two algebraic properties. One relates the matrix multiplication with the addition of matrices. This property is indeed called distributivity. The second relates the matrix multiplication with a scalar multiplication, and it states that these two different multiplications commute with each other. The first property follows from our theorem using lambda to be the scalar 1. The second property also follows from our theorem by noting in passing that multiplying a matrix by a zero matrix gives a zero matrix. Note that the size of the matrices must be consistent. We also remark that multiplying by a scalar lambda is the same thing as multiplying by lambda times an identity matrix. The property we have proven about the multiplication of matrices and its relations with the vectorial operations on matrices can be used to talk about an algebraic structure. Now, we use the term algebra of matrices in these lectures to designate the entire algebraic picture we have described about matrices. However, in mathematics, the term algebra has various specific meanings. By default, we understand the term algebra to mean associative algebra. An associative algebra over a field K is a quadruple A plus star dot, such that A plus dot is a vector space over K, while star is an associative operation on A which is distributive with respect to the addition plus, both on the right and on the left, and commutes with a scalar multiplication dot. Moreover, an associative algebra is said to be unital when it contains an element E, such that for all element A in our algebra, E star A is A star E is A. The operation star is called the multiplication of our algebra. As usual, when performing computation in an algebra, it is common to use simply juxtaposition instead of star to denote multiplication. Note that we do not assume that the multiplication is commutative. We also did not assume that any element of our algebra has an inverse for the multiplication, a notion which only makes sense anyway when the algebra is unital. In general, an arbitrary element of an algebra may not have a multiplicative inverse. In fact, it is easy to check that the zero element from an algebra must be absorbing for the multiplication, and thus does not have an inverse for the multiplication, putting aside the degenerate case where A is a singleton. The structure A plus star is what is called a ring. Thus, an associative algebra is at once a ring and a vector space, where the addition is shared between those two structures, and with an additional compatibility relation between the multiplication of the ring and the scalar multiplication of the vector space. While not all associative algebras are unital, if a unit exists, it must be unique. This is a standard consequence of associativity. Last, there are other types of algebras in mathematics, such as Lie algebra or Jordan algebras. Nonetheless, when we talk about an algebra without specifying which kind, we mean an associative algebra. The point of this digression into terminology is that the space of n by n matrices, that is the space of square matrices of size n, is a unital associative algebra. It contains an identity matrix, and we can always multiply together two n by n matrices. Thus, as we have seen, the multiplication of matrices restricted to the space of n by n square matrices will be associative and distributive on both the left and the right. It will also commute with the scaling of matrices. We call the resulting structure the algebra of square matrices of size n. Note that there is one algebra for each non-zero natural number n. We will discuss morphisms for these structures in a subsequent lecture. We conclude this lecture with an explicit formula to compute the product of two matrices. We place this result at the end since we do not need it to establish the basic properties of the multiplication. In fact, using it would be very clumsy. Moreover, this is just a compact form of the defining formula for the product of a matrix by a vector. There is nothing new here. We just present an algorithmic way to compute the product of matrices. Thus, if we multiply a matrix with entries A, J, L, where J is between 1 and n, and L is between 1 and m, with a matrix with entries B, L, K, where L is in the same range, and K is between 1 and p, then the entry of the product at some coordinate j, k, that is on the jth row, kth column, is the sum over L from 1 to m of A, J, L times B, L, K. The proof is immediate by applying our definition of the multiplication of matrices. Note that the product of an n by m matrix with a m by p matrix takes m times n times p multiplications. It is thus a costly computation. Multiplying square matrices of size n take n cube multiplications. For instance, simply multiplying two 10 by 10 matrices already takes 1,000 multiplication. There are advanced algorithms which, for very large matrices, can multiply matrices more efficiently, for instance, using the fast Fourier transform. But those algorithms are really not any better than the naive implementation given here, unless the matrices involved are really very large. It should be noted, however, that, for instance, in statistics, it is quite possible to have to work with matrices containing thousands of rows and columns. For such large matrices, much effort is dedicated to implemented multiplication of matrices efficiently. In general, not all non-zero matrices have a multiplicative inverse, or even a left or a right inverse. These notions are tightly related to the properties of the linear maps associated with the matrices. Indeed, invertibility corresponds exactly to the notion of isomorphism, while left and right invertibility correspond respectively to injectivity and surjectivity for the associated linear maps. We will study these matters in our next lecture on the algebra of matrices.